Okay, now I'm going to work out. I've worked out the expectation of x using the first derivative, which was this thing here, I think. Yeah, that one there. So now to work out the second derivative, sorry, to work out e of x squared, that's d by dt squared, differentiate it twice, m of t evaluated at t equals 0. There we go. So I've already differentiated it once, which is this formula here. So I'm going to differentiate it again. So it's d by dt of that thing there. See if I can remember it. np e to the t. np e to the t 1 minus p plus p e to the t all to the power n minus 1. And then close these brackets off here. Now then, we're differentiating with respect to t here, so these guys can just come throughout. So it's np d by dt of e to the t 1 minus p plus p e to the power n minus 1. Oops, which is that. Okay, and then we know that uv dash equals u dash v plus uv dash. Different people write it different ways. And this bit here is u, and this bit here, actually I'll put that in a different colour. I'll put that in red. This bit here is u, and this bit here is v. Alright, so the thing I've got is np times all this stuff here. So it's u dash v, well differentiate e to the t, it's just e to the t, times v, 1 minus p plus p e to the t to the power n, n minus 1. Plus this term here, so that's u, which is again e to the t, and then we differentiate this thing, so it's p e to the t times n minus 1 times 1 minus p plus p e to the t all to the power n minus 2. Close curly braces to match these guys here. Right, now we're cooking. Now what we do is we say t equals 0, and that's got a couple of consequences. The first thing is that well, e to the 0 equals 1. So this thing in the brackets will turn into 1 minus p plus p times 1, which is just equal to 1. So that's that bracket there and this bracket here. And the exponential terms vanish as well, which is nice. So what have we got? np times e to the t is just 1. Oh, that's just 1, isn't it? Plus p n minus 1. That's it. That's it. Well, I haven't forgotten everything. Look, e to the t times 1, which is this bit here, plus that term there is just a 1. P is there. That is a 1, which I don't even write down. N minus 1 from the differentiations there. This is just a factor of 1 to the power n minus 2, so it's just that. So that equals the expectation of x squared, where x is a binomial distribution of size n and p. Now, well, I think that result is quite nice. That's very nice. Well, we can start to do things with this. You might know that the variance of a random variable, I'll write that out again a bit more neatly. The variance of a random variable x equals the expectation of x squared minus the expectation of x all squared. Maybe I could prove that later for you, but anyway, we can use this formula now to do it, because look, we've got np times, what is it, 1 plus p n minus 1, 1 plus p n minus 1, that's that, minus np all squared. You with me? Alright, let's just evaluate it. It's np plus np squared, that's np, no, it's n squared p squared, isn't it? N squared p squared minus np squared minus n squared p squared. That's that. That's that. That minuses that, and that's that. So that cancels with that. That's nice. So that's equal to np minus np squared equals np 1 minus p. Ah, we've seen that before. You might have seen it like this, equals npq. So how about that? We have used characteristic functions, and I appreciate it looks like a lot of faffing about, but believe me, it's a lot less mucking about than trying to do it by hand. Let me show you how to get the expected value of x squared using direct numerical simulation. Well, what we want is sigma r equals 0 to n of n choose r p to the r 1 minus p to the n minus r times r squared. All this guy in brackets here. Now that is a pig to do. You can do it algebraically, but my goodness me, it is a pain in the neck. It's so much easier to use the moment generating function. So the way to think about a moment generating function is calculating it's the hard bit. Once you've done that, it's like an investment. Once you've calculated the moment generating function, or the characteristic function if you want to do things absolutely properly, excuse me, it's like an investment. Once you've done it once, you can get all this wonderful stuff dead easy, and we can even do the expectation of x cubed. And if you think this thing here is hard, which it is, if you make that a cubed, then it's like even harder. Okay, I'm going to stop there. Well, actually, the last screencast I will prove for you the characteristic function. It ain't as bad as it looks. It looks like a mess, but it's dead easy, really. Well, I'd say dead easy. It's not super difficult. You don't need complex numbers or anything. Right, done.